This is a walkthrough of the first practice exam for Physics 131 for the fall 2021 semester on one-dimensional motion. Car is traveling at a constant speed on a straight road parallel to the set of railroad tracks. A 1,000-foot train is traveling at a constant speed of 45 miles per hour in the same direction as the car is traveling. The car is catching up to the train. The child in the back seat of the car looks out the window and counts how long it takes the car to pass the train. She starts counting when the back of the last car is even with her and stops counting when the nose of the train is even with her. This takes 60 seconds. How fast is the car going in miles per hour? Let's draw a good diagram. We really need these to help us think. So there's the car. The car is the red car here. There's the train. Child's in the back seat. It says, oh, the car is going to catch up to the train. I'm starting to catch up right now. Later on, much later on down the road, the child is even with the front of the train, and she stops counting. All right, what now? We got to think. We got to figure out how to move forward. What can we do? This is the crucial part of the problem. This is the important part where we have to really think about what to do. One thing we can do is calculate how far the train went. We know how fast the train's going. How far does it go in 60 seconds? We can do that. So let's do it. We don't have to see all the way to the answer yet, but that's okay. We can just calculate it and then consider what to do next. This is a multiple step problem. Let's convert the units of miles per hour to feet per second. So 45 miles an hour, 1 hour divided by 60 seconds, that's 1. 5,280 feet in a mile, that's 1. And the miles cancel, and the hours cancel, and we get feet per second, 66 feet per second. How far do you go in 60 seconds? Well, 3,960 feet. That's how far the train went in 60 seconds. Let's add this to the diagram. Okay, so this is the distance the train went. The front of the train went 3,960 feet. Now what? Is the light coming on? Do we know how far the car goes over the 60 seconds? Now let's think about that. You probably know the answer already. Let's add this distance in there. All right, so there's the child in the back seat. There's the child in the back seat before. There's the distance the child travels. Let's add some vertical lines here. Child's lining up with the back of the train. Over here, child's lining up with the front of the train. Well, the car went 1,000 feet more than the train, right? There's the distance, length of the train right there. So the car went 3,960 plus 1,000. 4,960 over the 60 seconds. And if we know the distance and the time and its speed's constant, we can get the speed. 82.67 feet per second. We have to convert this to miles per hour. It says how fast is the car going in units of miles per hour. So we make that conversion and we get 56.4. That's the answer. One down. On to problem 2. Physics student drops a steel marble from 36 feet onto a thick steel plate. The marble rebounds to a height of 16 feet before falling a second time to hit the plate again. Use 32 feet per second each second for the acceleration due to gravity. Ignore air drag. We have 4 parts here. Let's not think about all of them. Let's do one at a time. Let's get rid of all those. Okay, that's better. One at a time. How long after the student drops the first marble will she have to drop a second marble so that the first bounce of the second marble exactly coincides with the second bounce of the first marble? Man. We need a good diagram here, and let's distinguish the marbles with colors. So we'll use blue for the first marble, red for the second marble. Here's the distances. We have 36 feet. That's where they're being dropped from. Fall straight down under gravity, ignoring air drag, and they bounce up to 16 feet. Now we can put in the paths of the marbles. The first one is blue, drops down 36 feet, hits the steel plate, bounces back up 16 feet, stops, comes back down, hits the plate for a second time. The red marble falls straight down, and this bounce right here coincides with that bounce. We need to calculate the delay between the release of the marbles, the blue and the red marbles. What's the delay? So let's calculate the time it takes for a marble to fall 36 feet when released from rest. So we have 1/2 AT squared plus VIT. It's released from rest. V initial is 0. Y is 36 feet down. The acceleration is 32 feet per second squared down. We can calculate the time. We just divide by 16 feet per second squared negative. Take the square root. Square root of 36 is 6. Square root of 16 is 4. The units come out to be seconds squared under the square root sign, which is seconds. And when you take the square root, 6 divided by 4 is 1.5. So 1.5 seconds to fall 36 feet. And our trusty equation is like this. Let's check it. All right. We're dropping something from rest. It's going to speed up at a rate of 32 feet per second every second. After 1.5 seconds, it's going 48 feet per second. After 1 second, it's going 32 feet per second. 1.5 seconds, it's up to 48 feet per second. Its average speed over this 1.5 seconds is 24 feet per second because it started at 0. The average of 0 and 48 feet per second is 24 feet per second. If it averages 24 feet per second for 1.5 seconds, it goes 36 feet. Ooh, it's right. Check. That's what we got. 36 feet for the distance. Okay, so now let's calculate the time it takes for the marble to fall 16 feet when released from rest. It reaches the peak and then falls 16 feet. How much time is that? Same equation, 1/2 AT squared plus VIT. Again, it starts at 0 because it's at its peak. And there's the acceleration due to gravity. It falls 16 feet. We can calculate the time, and we get 1 second for this fall. If it takes 1 second to fall from 16 feet, it must take 1 second to reach the peak. All right, so now we have the total time for the second bounce. But let's not rush. Let's not be careless. The blue marble takes 1.5 seconds to fall 36 feet. It takes 1 second to go back up to 16 feet. Another 1 second to come back down from 16 feet. That's 3.5 seconds. The red marble takes 1.5 seconds to fall 36 feet. The red marble takes 1.5 seconds. The blue marble takes 3.5 seconds for the second bounce. So it looks like we're done. The second marble has to be released 2 seconds after the first marble is released. That's the answer to part A. Now to part B. Part B, throw the second marble vertically at the same time she drops the first marble. Red marble's going up, blue marble's just being released. What's the initial speed of that red marble? So the first bounce of that red marble coincides with the second bounce of the blue marble, just as before. Instead of waiting to drop the red marble, we're going to throw it up. We're going to have to adjust the scale of our diagram because 36 feet would have gone up into the words. So we squished it a little bit because the red marble has to be going up. So let's put the red marble in there. We throw it up the same time we drop the blue marble. Goes up and then comes back down. This whole path has to take 3.5 seconds because the second bounce is also 3.5 seconds. We have to be careful here. Students assume that when the red marble gets here, it's going to take 1.5 seconds to fall, just like before. But now it has initial speed here. It's got a running start. This last 36 feet is going to take less than 1.5 seconds because it's not being released from rest. So we have to be careful. We know the total time of the flight is 3.5 seconds, though, so we can just do this. The only unknown is V initial. We know the time, it's 3.5 seconds. It falls 36 feet. The acceleration is minus 32. The time is 3.5 seconds. We have one unknown. We can solve for V initial y, and we do that. This is 196. Put it on the other side, makes it plus 196, and we get 45.7 feet per second, the initial speed of that second marble. Although it's not second anymore. It's released at the same time, but it's thrown up. I always like to check them because that sounds kind of weird to me, 45.7. If you throw it up at 45.7, it'll take gravity 1.43 seconds to remove all of that speed, because gravity sucks off 32 feet per second every second. It takes 1.43 seconds to stop it if it's going 45.7. Its average speed on the upward flight, it ends up at 45.7, ends up at 0, starts off at 45.7, the average is 22.9. If it does 22.9 for 1.43 seconds, it's 32.7 feet. So it goes 32.7 feet up, and it started 36 feet in the air. So now it's 68.7 feet above the steel plate, and it took 1.43 seconds to get there. Now it's going to fall from 68.7 feet from rest. So we have minus 68.7 feet. There's the acceleration. The initial speed is 0. It's not in there. And we can calculate the time. 2.07 seconds. So 2.07 seconds to come back down, 1.43 to come up. If you add those up, you get 3.5. It worked. Check. Part C. Part C asks for the height of both marbles versus time for the conditions in Part B. So co-plot the position of both marbles versus time. We'll use blue for the one that's dropped and red for the one that's thrown up. They both start 36 feet off the ground. They're released simultaneously. The first marble hits the steel plate for the first time at 1.5 seconds, the one that's dropped, the one that we're calling blue. Then, when it hits the steel plate, it instantaneously reverses directions, or as close to instantaneous as we want, goes 16 feet back up in another second, and then it falls back down, takes another second, 3.5 seconds total. We can't use one equation over the 3.5 seconds because there's this tremendous acceleration caused by the plate. When it's not touching the plate, it's always accelerating 32 feet per second each second downward. When it's hitting the plate, it has huge acceleration upwards. So we have to use two equations of motion. One from 0 to 1.5, and the other one from 1.5 to 3.5. Over the first 1.5 seconds, starts at 36 feet, 1/2 AT squared. V initial is 0. This marble is released from rest, falls straight down. At t equals 0, it's at 36 feet. So this is the equation of motion for the first 1.5 seconds. For the next part, we need to figure out what this thing rebounded from the plate with. We can use v final squared equals v initial squared plus 2ay. V final is 0. It goes up 16 feet, that's y. The acceleration is minus 32 feet per second each second. We can solve for v initial, and then we get 32 feet per second. So it rebounded from the plate with a speed of 32 feet per second. It's an inelastic collision. Lost some kinetic energy or thermal energy there. We can check this quickly. It takes 1 second to stop it. It takes gravity 1 second to stop it because it goes up at 32 feet per second. Gravity will take away 32 feet per second each second. It takes 1 second to get up. The average speed of 32 and 0 is 16. If it averages 16 feet per second for 1 second, it goes 16 feet, and that's how high it went. So now we have an equation for the height versus time for the time from 1.5 to 3.5. Y is 1/2. That's the acceleration. That's the time squared. That's the initial speed, and it started at the bottom. It started at y equals 0. With a graphing program, we can plot it. If you don't have a graphing program, you can plug in some t's here, and then put dots on the piece of paper, and then connect the dots. Let's just look at our graph. There it is. Start at 36 feet, accelerates, hits the plate at 1.5 seconds, comes back up, takes 1 second to get to the peak, which is at 16 feet, and it comes back down in another second, 3.5 seconds, hits the plate for a second time. The second marble is thrown upward at a speed of 45.7 meters per second. So there's no bouncing. The acceleration of that second marble is always 32 feet per second each second down. So we can just write the equation. 1/2 AT squared plus V initial plus the 36 feet that it starts at. And we can plot that. So there is the red marble that's thrown up at 45.7 feet per second. and hits the plate right here at 3.5 seconds, the same time that the marble that's dropped is hitting the plate for a second time. Part D, coplot the velocity of both marbles using neat, well-labeled axes. The first marble starts from rest, accelerates downward at 32 feet per second each second for 1.5 seconds. Then it hits the plate. The speed instantaneously reverses direction, going from 48 feet per second down to 32 feet per second up. It then accelerates, it's in free fall. It accelerates downward at 32 feet per second each second for the next 2 seconds, hitting the plate for a second time at 3.5 seconds. So here's the plot of that speed. Speed's going down, hits the plate, 48 feet per second, goes up to 32 feet per second, and now it's in free fall again. The red one starts off, throw it up at 45.7, and then the velocity just goes down by 32 feet per second each second. Here's the velocity of 0. This is when it's at its peak. Right there, if you remember, 1.43 seconds for the red one. The velocity of the blue marble switches directions twice. Here, when it hits the plate, and here, when it's at its peak. 1 second after it hit the plate. Red marble only switches direction once, when it reaches the peak. So the slope of these lines are all 32 feet per second each second negative. Except for this one here, when the slope is huge positive because the marble is contacting the plate. There's a bonus problem for this problem. Consider the situation in part B when both steel marbles are released at the same time. So this is part B. One is thrown upward at 45.7 feet per second. The other one is released. The one that's thrown upward has a higher speed initially. However, that ball is slowing down. The one that's dropped is speeding up. Eventually, the one that's dropped catches up to the speed of the ball that was thrown upward. The speed of the one that's dropped becomes bigger. When is that? When does that happen? So let's look at the graph and see if we can guess. All right. This one's thrown up at 45.7 and slows down. It's getting closer to 0. This one is released and it's getting farther away from 0. At 1 second, this one looks like it's going maybe 15. This one's going like 34 or something. It's got to be before that. At a half a second, this one's going about 30. This one's going about 15. Let me see, how about right when it crosses here, that's 20. But this one's already going faster than 20. It's got to be in here somewhere. Right about here. You see that? Maybe 22, 22. So what is that? 0.7? Something like that, 0.7 seconds? About right there. Once you have a good estimate, then you can calculate it. So actually calculate it and make sure you get about 0.7. I calculated it and I got 0.71. That's the first exam. Let's revisit problem 1 because there's a different way to do it. There's a trick to do it without calculating how far the train went. But I don't like to teach this because the goal is not to get the answer as quickly as possible. The goal is to develop thinking skills. So it's like going to the gym and saying, you know, if you use this pulley system, you wouldn't have to pull so hard or push so hard to lift the weight. The goal is to get the exercise, not to lift the weight. So the goal is to develop your problem-solving skills. But let's do it. Let's jump on the train. So now we're on the train and we're watching the car go by. So the train really isn't moving relative to us. So this is the initial position. We see the car catching up to the train because we're sitting right here on the train. And we count how long it takes the car to go the length of the train. and that takes 60 seconds. So we're in the reference frame of the train. The train is stationary. We can see the car go the 1,000 feet length of the train in 60 seconds. So we can calculate the speed of the car relative to the train. The car goes 1,000 feet in 60 seconds, which is 16.67 feet per second, which is 11.4 miles per hour. This is the car relative to the train. The train's going 45. So if we add the 45, we get the 56.4, which is the right answer. But it reminds me of when I was in graduate school and a professor said, this problem is much easier in paraboloidal spherical coordinates. I said, yeah, that's fine that it's much easier in paraboloidal spherical coordinates, but I don't understand paraboloidal spherical coordinates, so I'm going to do it in spherical coordinates. Right? There's no sense in doing some trick unless you're a Jedi master already. So you can use this. You can use this if you want, but you better understand exactly what you're doing.